So here's an example. I want you to try this one on your own. I want you to use that full conservation of energy equation. Go through it term by term in the equation and try to figure out what each term is equal to and then put it all together to solve. And I'll also mention that in this problem, you cannot solve this using forces and kinematics. Some of our problems that we're going to go through in these chapters, you can solve using kinematics and forces. This is one of them where you cannot, because there is a spring involved, and the force that a spring exerts is not constant, which means the acceleration of the object is not constant, which means you cannot use kinematics. Okay? Whenever there is a spring involved, you cannot use kinematics. You have to use the conservation of energy. If you try to use kinematics and you do it correctly, you're going to have to integrate your kinematic equation, and by doing that, you're going to derive the conservation of energy equation anyway, so you might as well just use that. Okay, so press pause, take some time to work through this, and then press play when you want to go through it again. Okay, so I'm going to solve this using conservation of energy. I'm going to set up my initial event and my final event. So I'm going to have my initial event be when the box is at rest, because I know a lot of what's happening at that point in time. And I'm going to have my final event be after the box has moved 50 centimeters, because that's when I want to know what the speed is. Okay, so we're starting when the box is at rest, and initially the spring is at the equilibrium position, which means I have no potential energy because the spring is not stretched and it's not compressed, so my potential energy at this event is 0. The box is at rest at this event, so my kinetic energy is 0. After I've moved 50 centimeters, I will be at a certain speed, so my kinetic energy will just be equal to 1/2 m whatever v final is squared, and v final, that's what I'm trying to solve for. There will be potential energy after I've moved 50 centimeters because now the spring is stretched out by 50 centimeters. So I'm going to put my x equals 0 at the equilibrium position of the spring. So I can write my potential energy stored in the spring as 1/2 kx squared, where x is the position of that box. So when the box is at x equals 0, my potential energy stored in the spring is 0. And when the box is at the position x equals 50 centimeters, I'm going to have to write that 50 centimeters in meters, so that'll be 0.5 meters. That is the x position of my box, and that is the distance that the spring has been stretched. Okay, so plugging in for my spring constant and the distance that the spring has been stretched, I find that the final potential energy of the system is 10 joules. Now I also want to know how much work did any external non-conservative forces do. In this problem, the only non-conservative force that is doing work is the tension. There is a normal force acting on my object, but the normal force is pointing straight up and the object is going to move to the right. That means that the normal force doesn't do any work. Gravity is not doing any work either because gravity is pulling down and the object is moving to the right. I would not include the work that gravity does here. I would include whatever happens with gravity in terms of the potential energy. But the potential energy due to gravity is not changing, so I'm not including that here. So the only work done by external non-conservative forces is the work done by the tension force. What is the work done by the tension force? Well, that's just equal to T, where that's how big the tension force is, that's how big my force is, times D, the distance the object moves while that tension force is acting on it. So my tension force is equal to 100 newtons, and the object moves 50 centimeters, or 0.5 meters. That means that that rope and the tension in that rope did 50 joules of work. So I'm going to include that in my equation. Now I also want to figure out how much energy did we lose due to the dissipative force of friction. So I'm going to calculate how much work did friction do, and I'm going to take the absolute value. So normally friction does negative work, but I'm going to just consider the positive value. So the work done by friction is equal to the force of the kinetic friction times the distance the object moves. Well, the force of kinetic friction is equal to mu sub k times the normal, and in this problem, the normal is equal to mg. That is very often true, but not always. Let's just think about what are the 3 cases when the normal force is not equal to mg. One case is when we're accelerating in the vertical direction. Another case is when there are other forces in the vertical direction. And a third case is when our object is on an incline. None of those are true, so we're in the very simple case where n is equal to mg. So now I can solve for the energy that's leaving our system due to dissipative forces. That's going to be equal to mu sub k times m times g times d. And I get 7.35 joules of energy is going to leave the system as thermal energy because of the friction. So now I can take my total conservation of energy equation and plug in for each term that I found, and I can finally solve for V final.